like to start my presentation with introduction of electrohydraulic actuator system. Electrohydraulic actuator system, which is EHS system, consists of three main components, which is electro motor, gear pump, and actuator. The working principle of EHS system is when servo motor rotates the gear pump generates a flow rate. This flow rate produces a pressure which changes the piston rod position. The movement direction of the piston is related to the rotational direction of the servo motor. EHS system is one of the most important drive system industries because it has a good capability in positioning, fast and smooth response, and also higher power density to handle the challenging work. However, this system is highly nonlinear due to its uncertainties such as column friction, viscous friction, and firm liquid cohesion, which leads to degradation of system in terms of force, pressure, or position tracking. First is the range of axle surface that injected into the system was from 0 into 10,000 Newton. MATLAB simulation will be used in order to analyze the performance of the system. A PID control is designed to control the system, and three types of methods were used in order to analyze the performance of the controller. First is dynamic method, second is a differential fine-tuning method, and third is a gravitational search algorithm. First, I started the project with mathematical modeling. Second, system modeling. After I completed with system modeling, I designed the controller, which is PID controller, and then tuned the PID controller with three different methods, which is GSM method, ZN method, and trial method. After that, I analyzed the controller performance based on the tuning method. The analysis of controller performance will be done until the satisfactory performance is produced. As I mentioned before, this project is started with mathematical system modeling. These are the equations of the EHS system. This project is developed using MATLAB simulation. The figure below shows the modeling of the EHS system. The axle instrument, which is FF that present in second order equation, is injected with three different values, which is 0 Newton, 5000 Newton, and 10,000 Newton. The table shows the parameter of this equation. As the system controller, the PID controller method equation is used to design the controller. This figure shows the PID controller that connected to the electrohydraulic actuator using MATLAB simulation. This figure shows the block diagram of the PID controller. The method that I've used in this project is trial and error method. This method started with shutting down the controller by making the parameter of the PID controller set to 0, and then increase the proportion gain until the output of the controller oscillates, and then set the integral gain to certain value which make the oscillation reduce. The steady error will be reduced by changing the value of the integral gain, but will increase the percentage overshoot, and then the direct gain will be increased until EHS system quickly react to the set point. This step needs to be done once the proportion gain and integral gain have been set to a desired value with minimum steady state error. Second is the Ziegler-Nichols fine-tuning method. The first step of this method is making the integral gain and the direct gain shut down or set to 0. At the same time, the proportion gain needs to be increased or decreased to obtain the steady state oscillation. The proportion gain that makes the system to oscillate steadily is known as ultimate gain. When the system is steady state, the ultimate period is the time is to take complete one entire oscillation. Once you get the value of all the parameters, the value of the proportion integral and the rest gain can be calculated using the formula given below. For the gravitational search algorithm, first step is generate the initial population and then evaluate fitness value for each agent. After that, update the G best and worst of the population and then calculate the mass and acceleration of each agent. After calculating the mass and acceleration of each agent, update the velocity and position of each agent. It will return the best solution if it meets the N criterion. In order to analyze the performance of the controller, three different external systems is injected into the system. First is 0 Newton for case 1, second is 5000 Newton for case 2, and third is 10,000 Newton for case 3. When no external instrument is injected into the system, The GC PID has achieved more precise performance compared to trial and error and sequence method. Based on table, GC PID provides the lowest percentage overshoot and the fast settling time from 0 second to 3 seconds compared to both tuning method. In the presence of GSA, the PID has produced the lowest steady state error, which is 0.003546. From 4 seconds to 6 seconds, the GSA PID has achieved the lowest percentage overshoot and fast settling time, which is 1.646% and 5.4 seconds respectively. Even though the steady state error is quite higher when compared to the other tuning method, it's significantly very low, which can be ignored. At the final point from 7 seconds to 10 seconds, the PID GSA has produced the undershoot and the produced faster settling time once again, which produces more precise performance other than the method. The PID GSA quickly achieved more precise performance of the design controller for the EHC system based on the table above. According to the graphic analysis, the GSA PID achieves the satisfactory performance of the design PID controller compared to other methods. The PID controller with the GSA for the EHC system track the reference segment smoothly and continuously compared to the trial and error and synchronous method. The drawback of synchronous and trial and error method is captured clearly when significant oscillations are produced during the simulation based on the figure. The oscillations are produced by both tuning methods. Synchronous and trial and error method can be noticed in each starting point, which is from 0 second to 3 second, from 4 second to 6 second, and from 7 second to 10 second. Controller. GSA PID has reached a faster response in settling time for every point to point, which is 1.2 second, 5.0 second, and 8.25 second. From 0 second to 10 second, no overshoot is produced, and the GSA can follow the reference trajectory. In addition, the steady state error of GSA at the 0 second to 3 second and 7 seconds and 10 seconds are lowest compared to another tuning method. Based on the table, GSA has produced no rise time and no overshoot but successfully follow the reference trajectory. In conclusion, the GSA PID can produce better tracking performance regarding rise time, settling time, percentage overshoot, and steady state error. Based on the graphic analysis, the PID controller presence of the trial and error method and the synchronous method puts up oscillation in every starting point of the shape of the reference input along the simulation process. The oscillation represents the output tracking error, whereas the GSA PID is able to follow the reference trajectory without making the oscillation in every corner of the shape of the reference input. According to figure, the GSA PID generates a smooth and continuous tracking output with the lowest tracking error compared to other tuning method. Therefore, GSA PID can generate satisfactory tracking performance for EHC system compared to trial and error method and synchronous method. Based on the table, the GSA PID produced the optimum performance when the 10,000 Newton is injected into the system. This is because GSA PID has a fast settling time at every point, which is 1.5 second, 5.8 second, and 8.72 second. At the beginning of simulation from 0 second to 3 second, the GSA produced no overshoot by following the reference signal and lower steady state error is produced. Even though the rise time steady state error higher when compared to the trial and error method and synchronous method, the PID GSA still produced the better transition response in terms of settling time and percentage overshoot, which is the lowest compared to other method. From 7 seconds to 10 seconds, the PID GSA achieves the faster response to settle the steady state without overshoot. Based on the figure, GSA PID generates a smooth and continuous output tracking with the lowest tracking error, whereas trial and error and synchronous method for the design controller produced almost bigger oscillation at every corner of the reference trajectory. Based on the figure above, the tracking performance of the PID GSA, which produced a continuous tracking output, is way better than PID trial and error and synchronous method. Therefore, GSA PID has achieved better performance in settling time, percentage overshoot, and steady state error, and gives the better tracking performance compared to the PID trial and error and synchronous method.